So we start now. I will go through all the questions because it's not that difficult. So the first one, give you 1 minute to read this, and we start. Is it clear? The side AB is only on the left. Right. Take a seat. So if the tank have the uniformly acceleration, which is from left to right, so how the surface will be? What the surface will be like? Yeah, so it should be higher on the left and lower on the right. So it could be like this. Yeah? It's clear. So how to make sure the angle of incidence? So if we know the acceleration, the AX is 5 meters per second square, and so we take an infinite part, a small part, for example here, a very small part here. We do the force analysis. So for this small part, on the axial direction, it should have two force, right? So the pressure from the left, which is F1, pressure on the right, F2, right? So we can use the Newton's second law, the F1. So which one is greater, F1 or F2?
F1.
Yeah, because it has the higher. So F1 minus F2 is equal to MAX, right? So in order to solve F1 and F2, we need to know the height. So we suppose that the height on the left is h1, and the height on the right is h2. So how does the pressure? So the P1, the pressure on the left is rho g h1. Yeah. And the pressure on the right, P2, is rho g h2. So we can solve the force. So the force on the left and the force on the right, could write it as P1 minus P2, and the mass. So the area of the force, which is, for example, W for white into the paper, and also the, oh, that's not H, so that one we suppose is a D, the length of the very small delta D, yep, which is equal to, so rho g h1 minus h2 W delta D equal to, how about the mass? The mass is rho v, right? So the density, and the v is, we suppose it's air on the bottom, the length. So it's rho delta D air, and W AX, right? So we can use that to finally got G H1 minus H2 is equal to LAX. So then we can get H1 minus H2 is LAX over G, which is that one. So we know the height difference. So so we can solve the length on the right. So we know that we know the difference. So the that height is half difference, right? And we know the original height, just added. So we got the length AB, which is 0.9. It's not it. It's, yeah, 0.9 plus half 0.12151 meter, right? So the AB could be solved. So the pressure on the AB, how to solve that?
Average force. Can we use average average force formula.
Yeah, you can use average force and also doing the integrations. Yeah, so for example, we do the integrations. The P is W from 0 to H1. No, sorry. From to LAB. The length of it should be equal to W 0 to AB rho G Z dz. So we suppose that the depth of it is D. So we got that one, and doing the integration, which is rho GW half AB square inside, and then we can get the final. Okay. So that one, the most important thing for this one is to just take the force analysis for a very small infinite volume, and to get the angle, to get the height difference, and then you can make sure what is the length of AB, and then doing the integrations to calculate it. Clear? Okay. So move to the next one. So it wants us to get the average pump flow exit velocity. So how we solve that?
Mass flow rate is equal to mass flow rate balance.
Yeah, and it's incompressible, right?
Yes.
So the volume flow rate of the pump filling is the same as the volume flow rate of the on the exit. So we can use that to calculate the volume flow rate, which is over that per second. So we got 1.07 cubic meter per second. We know the volume flow rate of the pump filling, and then the whole volume flow rate are moving to the exit, and we know the exit diameter, so we can use that to calculate the cross-sectional area of the exit. So the volume flow rate is also equal to the area, and U1, which we would like to solve. So which is pi d square U1, which is the second. Because we know the diameter is 3 centimeters, so we can get U is which is 1.452 meter per second. So that one, for this question, we use the continuity equation for the volume because it is incompressible. To solve it, and the next questions are all using the same the continuity equation. Make sense? Okay, so move to the next. So the two liquids, the water and the alcohol, comes into the mixing chamber, and mix together to get exit, flow out of from pipe 3. And we know the diameter of each pipe, and we also know the velocity of the alcohol and the water comes into the chamber. So, and also the specific gravity, which means the density is known, right? It wants us to calculate the exit velocity and the specific gravity. So how to calculate the exit velocity?
Use the same principle.
Yeah, because we just assume that the flow is incompressible. So all the density are the same. Actually, if it is mixed thoroughly, the density should be changed. But it's not that large. We just assume it's incompressible. So when we consider it's incompressible due to the continuity equation for the volume, we know that the A1 U1 plus A2 U2 is A3 U3, right? Which A is stands for the cross-sectional area. So U3 is A1 U1 plus A2 U2 over A3. So we can calculate it. Oh, sorry. which is pi and we can get the velocity. Yep. Based on the based on the continuity equation for the volume. And then how to calculate the specific gravity.
Use mass flow rate.
Yeah, so using continuity equations for the mass, we got rho 1 A1 U1 plus rho 2 A2 U2. We got rho 3 A3 U3. And thus we can got rho 3 is rho 1 A1 U1 plus rho 2 A2 U2 over A3 U3. And then just substitute all the value we know. So we got 922 kilogram per cubic meter for the density. And then we got specific gravity for the mixture water, for the mixture liquid, which is rho 3 over rho water, is 0.922. Okay, and we just assume the whole flow is incompressible, and use the continuity equation, conservation law for the volume to get the velocity at the pipe 3, and then use the mass flow conservation to get the density. Okay. And we go to the next one. Probably we go to question 5 first. That one could be quite complex, and we do something similar first. So the volume inside the tank increase because of we add water in. So like the former two questions, we suppose it is incompressible. So we apply the conservation law for the volume flow. For the volume, so the rate of volume increase is equal to net volume flow rate into the chamber. Yeah. So we know the area, the cross-sectional area of the tank. So we can calculate the rate of volume increase using the height the height increasing rate, and also the cross-sectional area of the tank. So the rate of volume increase is equal to A tank, which is the area, and multiply dH over dt. It is what we want to solve. And that one is the volume increase, which is equal to the volume into the tank, Q1 plus Q3, and minus the volume going out of the tank, Q2. And then we got pi half d square dH over dt, and V1 is pi half d1 square U1 plus Q3 minus pi half d2 square U2. Because we know the velocity of the fluid at pipe 1 and pipe 2, but pipe 3 we know the volume flow rate is given. And then finally we can get dH over dt is equal to half d1 square U1 plus Q3 over pi half d square minus d2 U2, right? And then we substitute all values in. Which is 0.9 finally. So that one, just to use the same increase of volume. But we know that actually it is an unsteady one, because the net volume is not zero. It has some change with time. So we can know the height, the changing rate of the height. Okay. And then we move back to question 4. That could be a little complex. And I'll give you 5 minutes for thinking about it. Oh, sorry. Actually, it's rho. The density. Yeah. Yeah, it's density. Sorry. I gave you the sorts using the mass conservation law. So the first thing to ask is which parameters changes during the variation. For example, pressure, density. Yeah. So it is different from other question because the density change. So we couldn't use the volume flow rate conservation law. So we use the mass flow rate conservation law. And we know it has some relations of P over rho, which is the constant. It wants us to give how pressure changes with T, right? Sorry, it's dP over dt. It wants us to do this, and we know that it has the relations of this. So first thing to do is that we can solve d rho over dt, right? We need to get that one. Okay, the first thing to do is use the mass flow conservation law. So the mass in minus mass out is equal to mass varies as time, right? That's the conservation law. So on the right term, we could write it. We extract the volume out because the volume is fixed. It could be written in volume d rho over dt. Because the density multiplied volume is mass. So just the density change, right, on the right term. And on the left term, there is no mass flow into. So that one is 0, right? So how to get that one? M out.
That the volume decreases by that amount.
Yeah. So we use the density at a specific time, at an infinite time, which is minus rho. That is the density at this time, a specific time. Multiply Q. The Q is constant, right? The density multiply volume flow rate is mass flow rate. So that one is the air going out of the tank. So and it is equal to the right term. Any problems about? And then the next thing to do is just to find, because we want to get the relationship between time and t, and in this we got rho and t. So now we move some terms to mathematics. So d rho over rho, which is minus q over volume dt. We move the terms to one side. We move the rho to the left and the time on the right. And then we need to do the integration. right? So based on this, we do the integration. What is the left term?
LNP.
Yeah, it's one rho, right, on the left term. And on the right term is Q over volume T. But we don't know the upper limit and lower limit, so we just plus the constant for this one. But now we know the initial density and the initial pressure. So initially, for time is equal to 0, we know that rho is rho 0. And we substitute A. We can get A is ln rho 0. Okay, finally we got ln rho is equal to Q volume T plus ln rho 0. It changes to the left. That one is ln rho over rho 0, right? And then we just take rho over rho 0 is equal to A Q over volume T. And that is how the density changes with it. Because we know that term, we can also write in P over rho is equal to P0 over rho 0. Also write into P over P0 is equal to rho over rho 0, right? So P over P0 is E okay. And now we know the P is 1000 Pascal. We just put it in. So the initial one is 100. So it is 1 over 100 equal to A minus 3 over 1 T. And then we got T is 40 seconds. So the important thing is to change that one to that one. We just move all the constant things outside the partial differential terms. Okay, so we'll move to the next one. And if you have questions, ask me later. And we got the final question here. So how to do that? Any thoughts? We know the profile on the right, the velocity profile on the right. But what is the same during the flow?
The density.
Yeah, the density, and we just want to use one thing to link these two. For example, the flow at the left and the flow at the right.
It is uniform, right?
On the left, it's uniform. It's a uniform velocity, and on the right, the velocity growing like the velocity profile like this. But the velocity profile has changed, but something not changed for the whole flow. The mass flow rate, yeah. So the mass flow rate on the left should be the same as the mass flow rate on the right. So on the left, it's easy to get the expression. It's just because of this incompressible, the density not changed, so the volume flow rate on the left is equal to the volume flow rate on the right. So how to solve the volume flow rate on the right?
Just put that u into the equation of mass flow rate.
You repeat the equation.
Yeah. So, for example, we take the infinite height dz here. We see the height of z. So that one, we can get the infinite volume flow rate inside, which is the u at that point multiply dz, right? And also the y into the paper, but we can just eliminate it on the left and the right. So that one is the volume flow rate, infinite volume flow rate. So we just do the integration from 0 to the height h. We could easily get, just substitute the velocity profile in, which is az, h minus z, dz. So that one is the volume flow rate on the right. We can solve that right? Then this is equal to the left. So the left volume flow rate is h u0, which is uniform, equal to left. So we can get the expression, the A is 6u0 over h squared. Right? And then we can calculate it. U0 is h is squared, which is 2004. So we got A. And we want to calculate the value of maximum velocity on the right. So where is the maximum velocity? In the central line, right? On the central line. So it's just the half height. So U max is equal to A. That one. Sorry. A height minus, that is